Welcome back. In our final unit, we want to take a quick look at quantum mechanics. Up until now, we have considered mostly what is known as classical physics. So quantum physics is required to understand the motion of submicroscopic objects. When considering very small objects like atoms and molecules, classical physics no longer accurately describes the motion, and this sometimes results in some surprising results. The main difference between quantum physics and classical physics is that things are quantized. That is, that energies and properties may have certain values but not others, while in classical mechanics, every value of energy is possible. So some of this should make sense. If we have one atom or 6 atoms, that's possible, but you cannot have half an atom. But this also occurs for properties like energy or angular momentum, which is a little bit more surprising. So the first proposal of quantized energy comes from the study of blackbody radiation. We looked at blackbody radiation earlier, but the notable thing is that if we follow classical mechanics, high-frequency vibrations have the same energy as low-frequency vibrations, and as a result, one would expect a hot object to emit light with the high frequency. That means that everything would glow white-hot, which obviously is not the case. The proposed explanation was that the energy of photons of light depended on the wavelengths, so high-frequency emissions were not possible due to this high energy. So Planck found that the energy of a photon was proportional to the energy in the frequency, and this proportionality constant was h, Planck's constant. This simple assumption had profound results. The idea that light was not continuous, but was emitted in discrete packets, what he called quanta of light, and this means that physics on a very small scale works dramatically different than at the macro scale. So in order to calculate the energy of a photon, we can use the energy of a photon is h, Planck's constant, times the speed of light c, divided by the wavelength. The speed of light divided by the wavelength is the frequency, so this is equivalent to what we did on the previous slide. In our next section, we want to use the energy of photons in electron volts, so, so we will use that hc in electron volt nanometers, which is 1240 eV nanometers. So if we divide this by the wavelength in nanometers, this gives us the energy. This also means if we want to find the wavelength from the energy in electron volts, we can take 1240 eV nanometer and divide by the energy in eV, and this gives us the wavelength in nanometers. So you have 2 questions to do, so they shouldn't give you much trouble. We're trying to set up quantization using results that should seem normal to you, so that photons have a set number of energy and that atoms and molecules come in integer numbers. So when we look at some of the less intuitive results of quantum, it's less jarring. Alright, so do your questions, and next we'll take a look at the photoelectric effect.